Hello, and welcome to another video in this series as together we learn the basics of Lean in order to write simple maths proofs. It's quite an exciting milestone today. We're starting what you might call part 4 of our series. So in part 1 we looked at very simple direct proofs, maybe looking at substitution. In part 2 we looked at proofs with a bit more structure, so using conjunctions and disjunctions, either in the proof objective or in the hypotheses. Proof by cases is the interesting one there. In part 3 we learnt about and practiced quite a lot using lemmas, and that's quite a common thing to do when writing Lean proofs, so it's good for us to see that and practice that and learn how it's done. We even wrote our own lemma and used it. In part 4, the final part, we're going to be looking at some more interesting kinds of proofs, which for me is quite fun and exciting. Today we'll be looking at proof by contradiction. In the future one we'll be looking at something like proof by induction, for example. So some interesting kinds of proofs. So today's Reductio Ad Absurdum, and we'll explain what that is. Let's dive in. So we've said we're going to be looking at proof by contradiction, and just the name sounds exciting, doesn't it? So let's think about a task. So we are given two facts, this one and this one. So this is an implication, the first one. It's saying if A is 5, then B is 6. So if this is true, then this is true. Not the other way around, but forward direction. So if A is 5, if we can establish that, then B is 6. And the second fact we're given is B is 7, which doesn't quite match up with this, so that's worth keeping an eye on. And we have to show this thing, and that's a symbol that we've not come across in this course before. It's a negation, and it reads as, it is not the case that. So it is not the case that A equals 5. So whatever follows this, the opposite is true. So we have to use these two facts to prove that it is not the case that A equals 5. So before we dive in and kind of follow a more formal kind of process for proving negations, let's kind of think intuitively, like if we weren't learning Lean, perhaps if we weren't even a student of mathematics, how would we approach it? Well, we'd be looking at this and thinking, well, we know B is 7, and we can see that if A was 5, then B would be 6, but it's not, it's 7. So if A was 5, then B would be 6, but it's not, because B is 7. So intuitively, it means that A can't be 5, because if it were A equals 5, then B would be 6, and that contradicts B equals 7. So you can see how that thinking, that intuitive thinking is correct, by the way, but within that is the kind of the proper formal approach. So let's just repeat that again. If it was true that A is 5, then B is 6 by this first fact. If it were true A is 5, B is 6, but it's not, because B is 7. So what have we really done there? We've said, let's assume A is 5. Where does that lead us? It leads us to B is 6, but that's a contradiction. So it can't have been the case that A is 5. So that actually, that intuition, which I've written on the slides if you want to kind of read it more slowly, that intuition is actually the formal approach that we're going to be taking. So let's kind of talk about that a little bit more. And the reason for thinking about the formal approach is that it's a standard method and recipe that's often applicable to proving negations. So this is the thing you have to remember, the recipe, the idea, but we will kind of draw a picture around it as well. But let's talk about it first. So to prove a statement is false, we show that that statement leads to a contradiction. And that's actually what we've done here. We've said, assume A is 5. We're supposed to show that it's not 5, but let's assume it is 5. What does that mean? Well, it means B is 6, and that's a contradiction. So it's led to a contradiction. So that's kind of what we've done here. And that's a kind of an English statement. Let's look at it in slightly more symbolic form. So if P is a proposition, a statement, to show that it's not true, if the negation is true, we need to show that the statement P leads to a contradiction. So I'm just gently introducing symbols. One, because it's good to see that. It's how we often write mathematics, but it also translates into lean. So in our case, P, that statement, is A is 5. That's the proposition. A is 5. And we want to show that the negation of that is true. So we want to show that it is not the case A is 5. So to show that, we need to show A is 5 if taken as a hypothesis, if assumed to be true, leads to a contradiction. Let's draw a picture because that's a lot of words. So let's compare the two approaches. So with standard proofs, we might have a bunch of known facts, hypotheses, and we have a proof goal and hypotheses. And what we do is we take logical steps to get us to the conclusion. So this is true by hypothesis, by assumption. These are things we are given as true. Then as long as we're following correct logical steps, each of these intermediate results, if there are any, are true, and then the conclusion is also true. So true statement, application of correct logic, true conclusion. So true hypotheses and correct logic leads to correct goal. That's not mathematical notation. What we're trying to do here is different. What we're saying is, in order to prove something is false, what we do is we take it to be true, assume it's true, and then we apply those correct logical steps. So the logical steps are correct, but it should lead to a contradiction, which is something that's demonstrably false. So let's look at this. The start is true, the steps are correct, and the conclusion is true. Here, we're having a kind of a different start. We're saying to prove this is false, let's assume it's true. So we have a false start, we have correct steps, and then we should get to a false conclusion. If we do, what do we think? False conclusion, the steps were correct. It must mean that this starting assumption was wrong. And if that's wrong, then the opposite is true. That's the idea. If that's for the first time you've seen that, feel free to kind of rewind and listen to that again, or read the blog, because that will explain it in words that are more carefully chosen. But that's the idea. So let me just summarize that. In a normal proof, we start with correct hypotheses. We have the application of correct logic to take us to a conclusion that's correct. So correct, correct, correct in 3 places. With this proof by contradiction, we have almost like a false start. We say to prove something is false, let's assume it is true. Let's assume that's true. We apply correct logic, see where that takes us, and it should take us to a contradiction, something that is demonstrably false. So if the application of logic was correct, what does that tell us? If it has led us to the contradiction, well, the logical steps weren't wrong, they were logically correct. So it must mean that our starting hypothesis was wrong. So if P was wrong, that means not P is what is true. So that's just replaying that a little bit. So let's write out in some small steps how we might solve that task. And it feels like overkill sometimes to write all these detailed small steps, because often we can do these things in just a few lines, pencil and paper, or in our head. But the idea is that this kind of writing takes us halfway to writing a lean proof, and that's why it's been training our brains over the last few videos to take us halfway to a lean proof, to think in terms of lean code. So we've got the given facts, which is a implication if A is 5, B is 6. The other given fact is that B is 7. Those are the two things that we start with. And our proof objective is to prove it is not the case that A equals 5. So following our recipe, we take this A is 5 to be true and see where it leads us. And ideally, it leads us to a contradiction. So we assume A is 5 is true for the purpose of contradiction. When you write maths proofs, you often write that. You say, for the purpose of contradiction. So we assume A is 5. And where does that take us? Well, we know from the first given fact that if A is 5, which we're assuming now, then B is 6. Cool. So we've got B is 6. B is 6 is not 7. That's simple arithmetic. So B is 6, but it's not 7. You and I can look at B is equal 6 and say, well, clearly it's not 7. When we're writing the level of detail required for a lean proof, we need to be just a little bit more detailed than that. So we can say B equals 6 means B is not 7. B is not 7 contradicts B equals 7. Those are the two contradictions. Yes, we can say B equals 6 contradicts B equals 7. But to be even more clear, just in case somebody's being really obstinate, we can say B does not equal 7 and B equals 7 are contradictions. So yes, it's being pedantic, but there's a reason for that, and it's how lean will work when we write the lean code. So we've got a contradiction. So if we've followed correct logical steps and the conclusion is a contradiction, that means the assumption was wrong. So assuming A equals 5 was wrong, and therefore the opposite, the negation of that, is true. It is not the case A equals 5. Why did I pause there? We won't get into it today, but there is a language around opposites and negations and contrapositives and inverses, and they have specific meanings. So when I said the opposite, I was not being very careful with my language. The correct language is the negation, and that's the easiest one to think about. Actually, it just means plonking it is not the case that in front of the statement, the proposition. If you want to look it up, it's kind of interesting that a contrapositive is not the same as an inverse, which is not necessarily the same as, I think opposite is not that clearly defined, but negation is definitely a thing, and it's the easiest one to understand. So that's the maths proof. Do we need to explain that any further? I think I will, just because it's the first time we've done this. So let's do that in pictures. So we're given A equals 5 implies B equals 6, and we're also given B equals 7. These are the two things we're given. So we want to prove it is not the case that A equals 5. That's the thing we want to prove. So to prove a negation, we take the statement that's being negated, and we assume for contradiction. That's the magic phrase you'll see in proofs, that A equals 5, and let's hope that leads to a contradiction. What does this give us? Well, by this implication, a equals 5 gives us b equals 6. And we can see that b is 7 here, but b equals 7. So b equals 6 means b is not 7. And these two things contradict, like visually you can see them. B is 7, b is not 7. So that's a contradiction. And therefore the assumption was false. So if a equals 5 is false, its negation is true. And that is the proof objective. So just talking about it in a different way there. And I'm only repeating that because it might be the first time you've seen that. So the title was Reductio Ad Absurdum, which sounds like a magic spell from a famous fiction series. It's actually Latin for reduction to absurdity, and it's quite a nice thing to know. So it's a proof where you lead to a conclusion which is clearly absurd or false, so or a contradiction. So here the absurdity is the notion that b is 6 and b is 7 are both true, which can't be the case. And just for clarity, when we say a contradiction or something that's false, that's equivalent. So when something is false, it's because it contradicts something that's known to be true. So just in case it wasn't clear, when we say leading to a contradiction, that's the same thing as leading to a false statement, because it's false because it contradicts something that's known to be true. So what I'll do today is I will use the Visual Studio Code because it's just got nicer feedback, and talk through it because there's a few new things in here. So all the code is available online on GitHub, so feel free to kind of download it and experiment with it. Let's talk through it briefly. Let me see if I can make the font a bit bigger. Yep. So we've got the usual declaration of variables, a and b as natural numbers. We've got two hypotheses, H1 and H2. The first is an implication, so a equals 5 implies b equals 6. And the second one is simply a statement that b is 7. So that mirrors our task. And our proof objective is the negation of a equals 5. So it is not the case that a equals 5. And that that negation symbol, you type /neg, and your lean aware editor, whether it's the online one or this one or a different one, will turn that into a negation. So how do we proceed? I mean, we can't build up to this easily from these given hypotheses, and the recipe we said we'd follow is to take a equals 5 and assume it's true for the purpose of contradiction, and see that it leads to a contradiction. Is that possible with lean? Well, the answer is yes, it is. And the way we do that is to use the intro keyword. And that's actually quite a flexible thing. It has different uses, and we'll see that in future. What it does here is it looks at the negation of the goal and turns the negated statement a equals 5 into a hypothesis, and it also turns the goal into false, which means we have to prove a contradiction, we have to prove something's false. So can you see, we start with it is not the case that a equals 5. After intro G, we have a new hypothesis G where we assume it's true. A equals 5 is now assumed to be true there, and our proof objective has changed from it is not the case that a equals 5 to it says false. So we have to prove an inconsistency, a contradiction. It doesn't matter how we do it, as long as we end up with one, and that's sufficient. So that's what this proof objective of false means. I'll jump right to the end to say that once we are ready to say there's a contradiction, the keyword contradiction resolves that and says, right, you've now proven false, you're done. So between intro G and contradiction, we have to arrange for a contradiction to be apparent. And the way we do that in Lean is to have two hypotheses in the goal state that are direct contradictions of each other. So one is, let's draw a picture. So in Lean, to prove a contradiction, we have to have in the goal state a hypothesis, let's say H1, which is some statement P, and another one, you can have different names, the names don't matter, which is the negation of that. So once we've got that, it is really clear, like visually we can see that, that's a contradiction. P is true, and the negation of P is true, that's a contradiction. So it could be that H1 is A equals 5, and H2 is not the case that A equals 5. That's an example. Another one could be H1 is X is more than 7, and it could be that H2 is, it is not the case that X is more than 7. Now notice they are exactly the same except for the negation. So we're not in the world of proving that X is less than or equal to 7. That's not how it works. It has to be lexically the same. So written down, typed in, it's the same, but one has this negation in front of it. So that's all we need to do. So from intro all the way up to contradiction, in between those two, our code has to just arrange for the appearance, the registration of two hypotheses, one which is the negation of the other. So that's what our code has to do. And that's what these two lines do. So let's look at them. The first one is applying our implication hypothesis to our new hypothesis that A equals 5. If A equals 5, then B equals 6, and that's what this turns G into. G starts as A equals 5, and that implication then turns into B equals 6. So we've seen that in our maths proof. B equals 6. Now looking at this, you can see B equals 6 and B equals 7. To us, that's contradictory, but we need to remember to write it in the form P and negation of P. So we need to either have, well, let's see what we do. We create a new hypothesis, H2X. I'm just using X to say it's a negation. And we're saying it is not the case that B equals 7. So that will contradict H2, B equals 7. How do we justify that? Well, the linear arith tactic is quite capable. It will look at this one and it will say B is 6, and from that it will work out that it is not the case that B is 7. How it works is a little more complicated, but we don't need to worry about that right now. For now, we'll just learn that linearith can do linear arithmetic. You know, we've already seen it justify proof steps like add 1 to both sides. It can take this and say B equals 6 and jump to it is not the case that B is 7. So that will give us the hypothesis that it is not the case that B is 7. So we've now arrived at two directly contradictory hypotheses. B equals 7, and it is not the case that B equals 7. And that's in the form that's ready for the contradiction tactic to say, yep, that's a contradiction. It won't do it on just these two, B is 6 and B is 7. We have to get it to that state. And once that's done, that's it, you've proven it. You've proved a contradiction, and that means that A equals 5 was a false assumption, and therefore the negation, it is not the case A equals 5 is true. That's a lot of talking, and you should experiment and practice this yourself, because I suspect that it's not something that you may have done lots of. If you have, that's great, fantastic. If you haven't, the best way to get used to this is to try it a few times on simple exercises, simple examples that you've made up yourself, and they don't have to be complicated, just to see this working. And the exercise at the end is a good opportunity to do that. So if you wanted to read a little bit more slowly what those explanation of that was, the slides have it if you want to read the slides, and the blog also has it as well. So yeah, we're just talking, just to refresh that, we're using intro to assume the false statement is true, and then we use the goal is set to false. So that's a thing worth recognizing. Whenever you see a goal of false that we saw here, like if I'm up here, see the goal is false, that means we have to prove a contradiction. And we have to arrange for a hypothesis, say P, and another one that says the negation of that, whatever P is. The P's have to be the same. Once we arrive at that, then we're done, and the contradiction then resolves it. So the contradiction searches the current hypotheses and looks for any that are direct negations of another, like that. So that's the only thing that might catch you out, is if the goal state was x equals 5 and x equals 6, we might think that's contradictory, but that's not ready yet for this contradiction tactic. We need to get it to a place where x equals 5, and it is not the case that x equals 5. That's what we need to do. It's worth, again, looking at the Infoview, because it's a great way of keeping track of your own proof and what Lean actually thinks is happening, and it's kind of gives you an insight into how the proof is working. So just before intro G, we have the goal, which is it is not the case A equals 5. After intro G, we have that statement assumed to be true. So it is now introduced as a new hypothesis G, A equals 5, and the proof goal is now false. So that's the effect of intro G. And just before contradiction, it's worth noting, that we can see two directly contradicting hypotheses, H2 and H2x there. So that's worth just checking. You can see that in the Infoview. As I said, the Infoview is really valuable when you're writing your own proofs, because it just checks that what you think is happening is actually what Lean thinks is happening. And the easy exercise is, well, we say easy not to be patronizing, but to say that the maths is not going to be difficult, and it's practice using the Lean idea. So here we've got, we want to prove that it is not the case A equals 5, same as the other one, but we're given a different set of facts, and we're given a bidirectional if and only if statement, and then B is 6. So let's just draw a picture of how we might do that. I'm not going to solve it for you, but I'll just explore the problem a little bit. Actually, let's compare them. So previously we had A equals 5 implies B equals 6, and we had B equals 7, and we wanted to prove that is not the case A equals 5. Here we've got the same. We have to prove that it is not the case A equals 5. So we have A is more than 5 if and only if B equals 6, and we're given B equals 6. So it's slightly different. Here the path was assume A equals 5 is true. That gives B equals 6, which contradicts B equals 7. What are we going to do here? Well, this is bidirectional, so it's true in both directions. We're given B equals 6, which means we can then go in the backwards direction from B equals 6 to have A is more than 5. And A is more than 5 contradicts A equals 5. So that's just a hint there. So here, again, it's useful to see these comparisons. Here we had assume A equals 5. That gives us B equals 6. But B equals 7, contradiction. Here we're going to assume A equals 5, that one, for contradiction, and then we say the backwards version of that bidirectional implication. So you remember we'll have to, you might have to remind yourself of how to pick a direction and then apply it. So there's a previous video, look at the blog if you like, on how to select the forward and backward directions. So here we're going to use b equals 6, which is given, which tells us that a is more than 5, but that contradicts a equals 5 contradiction. So that's not in lean code, that's in us using pen and paper, but that'll be the idea. So have fun with that. Any questions, do comment and we'll have a discussion. But I hope you enjoy that. We're starting to look at some interesting kinds of proofs now, and I think proof by contradiction is really powerful. It's actually powerful for several reasons, because with a more constructive direct proof, you almost have to kind of have a path that goes from known facts to the target, whereas with a proof by contradiction, you're almost starting with the opposite of the proof goal and then leading to any contradiction. It doesn't matter which one. So in some ways it's more open, and you might heuristically say, well, there's more likely of chance of success. I can't prove that, but it feels like they're more effective than you might think, and there's lots of really interesting proof by contradictions out there. Some of them are quite famous, like the proof that square root of 2 is irrational. That's done by proof by contradiction. You start off by assuming the square root of 2 is rational and see that that leads to a contradiction. Yeah, look it up, that's quite a nice one. Great, we'll see you next time. Bye.